So let me show you a few details about analyzing the frequency of the pressure fluctuations associated with a vortex shedding flow meter. So this is the geometry, and we've got this rod in the flow. The flow is going from left to right, and as the flow goes around this rod or the circle, it creates this oscillatory pattern that has a periodic fluctuation in pressure. And so what we want to do is measure the pressure and analyze it to see if we can correlate the frequency of the pressure fluctuations to the velocity. So what I did was to put in a cut point, and it's right there. So I'm going to measure the pressure on the side of this cylinder. We go and set up the cut point and use a point plot here, and this is the pressure for a flow rate of 1 meter per second over about 6 seconds. And you can see when we started up, the pressure is kind of erratic here. There aren't very many points in this plot, and that's why it's so jagged. But you can see it's not really periodic. But once we get to about 3.5 seconds, we get this much smoother plot. It's smoother because I calculated more points after 3.5 seconds, but you can see it's quite irregular. Looks like a sine wave. And so with this kind of a signal, we can measure the period. We can take the inverse of that to get the frequency, and then we can correlate that to the flow rate to see if this thing could really function as a flow meter. So the way I did the analysis was to copy the image here and pasted it into PowerPoint. And so there it is. And let me see, I'm going to just use PowerPoint in kind of the editing mode. So if I zoom out here, you can see a little bit better. This is just the PowerPoint slide. And so I want that one. So this is just pasted in there from COMSOL, and then I draw in this rectangle. And what I want to do is get the period, which is the length of time for one wave. So I go from peak to peak and trough to trough, and you can see it's quite a regular periodic wave right here. So that rectangle allows me to preserve that length, and I come down here and measure it, and you can see that it corresponds to 0.5 seconds, half a second in time, peak to peak. So I ran a few more analysis at different flow rates. This is a flow rate of 1 meter per second, so I ran 2 other flow rates, and this slide shows those results. This is the one we just saw. It's got a period or a flow rate of 1 meter per second, and what I did was to calculate the frequency, and frequency is the one cycle, and that's the period that it takes for one cycle. So it corresponds to a frequency of 2 hertz. So I did a slower flow of 0.5 meter per second, and this is the pressure fluctuation for 0.5 meter per second, and that lines up like so. See how it kind of jumps around like that? What you want to do to get a little better, a little more accurate assessment is to go in here to under picture tools to align and the grid settings. Okay, I thought that it was snap objects to grid. I thought that was on, but it's not. So let's just try zooming in, get a little bit closer, and see if we can move this a little more accurately. Yeah, that's better. It was just I was zoomed too far out. So there's peak to peak. We measure that, take it down here to the time scale, and you can see that's just about exactly 1 second. So the frequency is 1 cycle in 1 second, or 1 hertz. And I can go down here. This is a faster flow rate, 1.5 meters per second. That was the flow rate, the velocity that I used in the COMSOL model. And here's the signal that I pasted from the COMSOL model, and I determined the the period peak to peak again, and I had to estimate that. It looks to me like it's about a third of a second. So one cycle in a third of a second is a frequency of 3 hertz. Okay, so now what we're trying to do is see if this structure, this circular rod or cylinder in a flow, can cause these Kármán vortex streets that result in a fluctuation in pressure that correlates to the flow. And if it does, then we could measure the pressure and use the frequency of the pressure fluctuations to estimate the flow rate. So I plotted up these results, and here's what you get. Zoom out a little bit, and there's the flow velocity that I used in the simulation as a function of the cycles per second of the pressure fluctuations. And you can see there's a nice correlation. We only have 3 points here, so it's not, well, it would definitely be good to have more data, but it looks pretty good. We get this nice relationship where the velocity equals half of the frequency in cycles per second. So this is quite encouraging in our quest for a vortex shedding flow meter. So this analysis we can do in a pretty short amount of time, and if we were considering a vortex shedding flow meter, then analysis like this one would be a good kind of proof of concept, and we might want to then go and try it in the laboratory.